So let's move straight on to our second presenter, also from IIASA, Ulf Dieckmann. Ulf is the leader of the Evolution Ecology program, and he will tell us about meeting the challenges of securing aquatic food resources. So we move from land to ocean. Ulf.
Thank you very much, Carlos. It's a pleasure to be here, and I would like to contribute to the session by taking a joint look under the surfaces of the oceans and see how the marine life and also the life in other water bodies is contributing to the issue of food security and supplying future generations with robust sources of nutritional income. Aquatic food resources are key providers of animal protein for a large fraction of humankind. Many economies and communities, in particular in developing nations and coastal regions, depend on fisheries. Unfortunately, however, rampant overfishing on open access, open fisheries is causing serious problems. And while this is widely recognized, the analogous problem in the context of freshwater systems is only gradually receiving commensurate attention. Also in these systems, there are serious problems of overconsumption. Let me now review together with you a few key facts that put into context the challenge of securing food security in the aquatic domain. Seafood is a primary source of animal protein for more than 1 billion people. And this is not only a nutritional issue, but also a socio-economic one, because fishing, aquaculture, and related industries support the livelihood of 700 million people around our globe. And in Western countries, I have the impression that we often think that this is a matter of industrial-scale fishing and large companies reaping benefits from the oceans. And therefore, it's important to recollect that it's only 2% of the motorized fishing boats that are of industrial size. So there's a lot of artisanal and regional community fishing going on that contributes an important dimension to this challenge. The total annual revenue from world fisheries is $2.25 billion. Total annual production is 155 million tons, and to give that a context, that translates into an average annual per capita fish supply of 19 kilograms per person. And you have to imagine that some people obviously consume less than the average, but others then make up by consuming more. So this is quite a substantial contribution to the world diet. Fortunately, production growth in the past 50 years has been enormous, amounting to 480%, which is often referred to as our successful conquering of this blue continent that are our oceans. And one can argue that this conquering actually has been a bit too successful and that we are overstretching the natural boundaries of these marine systems. Another important development is that the supply of aquatic food has gradually shifted from capture fisheries in the oceans to aquaculture, which are often coastal enterprises. Today, aquaculture supplies 40% of total production, and in China, one of the pioneers and proponents of aquaculture intensification, it is even 65% of the food production from aquatic sources. During the past 30 years, the capture production from fishing in the oceans has actually plateaued. We have reached a ceiling, and this is a natural indication of a planetary boundary served to us by the statistics. For the last 3 decades, there has been no increase in the biomass extracted from living aquatic food resources. In contrast to that, aquaculture production has risen 12-fold. So most of the recent rise in production over the past 15-20 years comes from aquaculture. And we are now seeing that this is also obviously no panacea, because massive environmental problems from organic pollution and disease accumulation are threatening the aquaculture industry. And finally, it's worth remembering that 50% of our fish stocks are fully exploited, but even a quarter of them are overexploited, collapsed, or recovering from overexploitation. So again, this is a reminder that the planetary boundary in this regard has been reached. Now, to deal with these challenges, we have to look at fishery systems. And that is a perfect challenge for the general approach and methodology IIASA has developed over the years. We have the natural system with the target fisheries, also the surrounding fisheries and the ecosystem embedding. That is yielding ecosystem services of various kinds, defined, for example, by the Millennium Ecosystem Assessment. These are used to monitor the state of the system and to choose appropriate managerial actions in a third component of the system, which is then regulating the actions of the fishermen, which are also directly responding to the status of the ecosystems, and closing the feedback loop by exerting the fishing pressure. So these feedbacks are creating uncertainties and non-linearities that require an integrated assessment of the kind that IIASA is offering. IIASA's main contributions to this area come from three domains, which I would like to highlight here in terms of three vignettes of research that we have done at IIASA, which in my opinion also highlight the directions for promising future research where further effort is needed. The first is on process-based models. These are in contrast to the traditional statistical models and are needed for coping with nonlinearities, uncertainties, and regime shifts. Whenever you have to extrapolate, a statistical model is of limited use, and a process-based model is often the wiser choice. Secondly, we have to face the fact that by fishing, we are not only changing the numbers of fish in the sea, but also altering their heritable characteristics. We are forcing these fish stocks to adapt. And this is so far a blind spot in international fisheries management that is an urgent need of being overcome, and we at IIASA have worked on this for the past 10 or 12 years. And finally, all this needs to be brought together in integrative assessments, because only these can provide quantitative and transparent basis for stakeholder consultation and reconciliation. Let me now run on 3 slides through examples for these 3 domains of attention. The first example is on process-based models and is chosen to illustrate some work on a very valuable European stock, the Northeast Arctic cod, arguably the most important European fishery. Here the standard statistical models are problematic because they are not so suitable for extrapolating into new regimes that have not currently been sampled in the historical data. Also, standard age-based models are not entirely suitable under the conditions we are facing because they are not good in dealing with variable growth. So, in fact, we have found that growth turns out to be varying in the stock, not only with temperature, but also with the stock size, through a process that ecologists refer to as density dependence. You might argue that this is such a basic phenomenon that several national fisheries research institutes around the world should have tackled it. This is not the case, and I think the more fundamental, more process-based perspective provided by the systems thinking at IIASA is triggering us to do these analyses. So the result is that a 2% increase, a 2-degree centigrade increase in temperature is expected to cause a 25% increase in the growth of this stock. So that's a high sensitivity for this biostatistical response, and we have to regard the 2-degree increase as also conservative for the expected climate change in the Barents Sea, which is a habitat of Northeast Arctic cod. With that, let me move on to the second example to illustrate the importance of fisheries-induced evolution through our work on the collapse of northern cod. This is regarded by many as the worst disaster in modern fisheries management. A bountiful fisheries which have been exploited for centuries, starting with Portuguese boats going across the Atlantic and bringing cod back to Europe, has collapsed in 1992 through overexploitation, first of the international fleets and then by the Canadian fleets. Heavy exploitation favors maturation at smaller size. When you're not likely to be alive next year, it's better to get your offspring out this year to leave an imprint on the next generation. We have documented, as expected, a 15% drop in age at maturation and a 30% drop in size at maturation. This is an evolutionary change that is not captured by traditional approaches to managing fish stocks. It's an early warning signal that occurred before the collapse, and if the techniques had been available for detecting this signal, it might have cautioned fisheries managers in Canada to treat the exploitation of this stock with greater care. What is particularly worrying about fisheries-induced evolution is that it is very slow and very difficult to reverse. Our models indicate that it often takes 5 to 7 times longer to reverse the trend than to cause them. Finally, an example on integrative assessments. We have worked with our Norwegian colleagues on Barents Sea capelin. This is the largest capelin stock in the world and was the largest Norwegian fishery until it collapsed in 1986. Our assessment tries to incorporate socioeconomic dimensions beyond the traditional metrics, which is why we include yield, profits, employment, and the ecological impact. We also go beyond a single stakeholder analysis and try to address the conflicts and the potential reconciliation among stakeholders, including conservationists, including artisanal fisheries activities and industrial fisheries activities. What we find is that the two control variables that can be used to regulate the fisheries, namely on the vertical axis, the minimum size limit, so these are the smallest fish you're allowed to extract and land, and on the horizontal axis, the proportion, the annual proportion extracted from the remaining stock, have a response surface shown here in gray scales that is very interesting. In fact, in this yellow region, 70% of the maximum utility for any stakeholder is reached. So the least satisfied stakeholder in this region, in this parameter region, reaches 70% of the maximum utility. And where are we today? We are far below. The status quo is actually not emphasizing minimum size limits, but one could argue barking up the wrong tree by discussing total allowable catches and quotas on an annual basis, and this is not the optimal way of reaping societal benefits from this stock. And finally, all this is connected in the context of improving fisheries policies. We are strongly involved in an international expert group on fisheries-induced evolution, which is part of the scientific advice provided by the National Council for the Exploration of the Sea, which is the main science advisory body on the North Atlantic. We have proposed a new tool for enhancing traditional fisheries management, which we call evolutionary impact assessment. It was published in Science a couple of years back. And one little success of these activities is that monitoring maturation evolution has now already become a binding EU requirement. And both in this expert group at IIASA and at IIASA, we are now working on further integration of the 3 dimensions which I've highlighted as topical for the future, namely process-based modeling, evolutionary induced changes to fisheries, and the socio-economic dimensions of fishing. And with that, I thank you for your attention.